In this problem, we're told that a charge of 5 microcoulombs is at the origin, and the second charge of negative 3 microcoulombs is on the x-axis, 0.8 meters from the origin. We're going to find the electric field at a point on the y-axis, 0.5 meters from the origin. So let's first start by drawing a diagram. We have at the origin a 5 microcoulomb charge, so I'll label this as Q5. And then we have on the x-axis 0.8 meters away. So I'll go 1, 2, 3, 4, 5, 6, 7, 8. 0.8 meters away is a negative 3 microcoulomb charge. So I'll label that as Q3. We want to find the electric field on the y-axis 0.5 meters away. So I'll put an X there. There's no charge there, but we can still find the electric field. It doesn't have to be a charge to locate or to calculate an electric field. What we're going to do is find the electric field from the 5 microcoulomb charge, and then find the electric field from the negative 3 microcoulomb charge, then add them together and get a total. So let's find the electric field from the 5 microcoulomb charge first. Our equation is KQ5 over R squared. Now, K is Coulomb's constant. That's 8.99 times 10 to the 9th newtons times meters squared per coulomb squared. So based on that, we need to have our charge in values of coulombs, not microcoulombs. So micro means times 10 to the negative 6. Now we need our distance, and our distance from that charge is 0.5 meters. Don't forget that it has to be squared. We get a value of magnitude as 179,800, and the units then would be in Newton per coulomb. We also need a direction. Now, electric field points away from a positive charge. So if I stand here at my X, and I point away from that positive charge, I would be pointing upward. So you place yourself at the X, then think about, do I point towards it, or do I point away from it? And the electric field points away from a positive charge and towards a negative charge. Now we're going to find the electric field from the negative 3 microcoulomb charge. So again, it is KQ3 over R squared. K is again 8.99 times 10 to the 9th. We're going to leave off any positives or negatives here with our charges. We just always make it an absolute value. But again, it's micro, so we convert to times 10 to the negative 6. Now my distance, though, I'm going to have to get using the Pythagorean theorem. So Pythagorean theorem says a squared plus b squared equals c squared. And the two sides were a half and 0.8. And so I get 0.943 meters for that distance. So this distance here is 0.943 meters. Don't forget that that has to be squared for your distance. And the electric field from the negative 3 microcoulomb charge is 30,300 newtons per coulomb. But again, we need a direction. So if I stand at the X, if I'm at the X, and I want to figure out the electric field points towards a negative charge. So I need to draw an arrow pointing towards that negative 3 microcoulomb charge. That would be then down and to the right. But I need an angle associated with that. So I need to find this angle, and to do so, I'm going to use my inverse trig. Let's go back here to our scratch paper here. So the inverse tangent of the opposite side, and we see that the opposite side is 0.8 meters, divided by my adjacent side. We see that our adjacent side is 0.5 meters. So the inverse tangent of 0.8 over 0.5 is our angle, and we get our angle to be 58 degrees. So this angle here is 58 degrees. I'll label on both diagrams. Now, because this electric field is at an angle, we're going to have to find its two components. I'll label them as the parallel and the perpendicular component. Now, we're going to find those parallel and perpendicular components using our sine and cosine functions. So we have first, let's find the parallel first, but I want to redraw this here. Here's our 58 degrees. Our hypotenuse was the electric field that we found, 30,300 newtons per coulomb. And we're going to find the parallel and the perpendicular component. Now to find the parallel and perpendicular component, we'll use our sine and cosine. Let's find the parallel first. So the parallel component is the opposite side, so that'll be sine. So sine is opposite over hypotenuse. And we get that the parallel component comes out to be 25,700 newtons per coulomb. And the direction is to the right, because this overall was down and to the right. Now we'll find the adjacent or perpendicular component, and that'll be cosine, because cosine is the adjacent side divided by the hypotenuse. And so we get the perpendicular component comes out to be 16,058 newtons per coulomb, and that would be down, because the overall total was down and to the right. So let's go back here and write down those two components. The parallel was 25,700 newtons per coulomb to the right, and the perpendicular component was 16,058 newtons per coulomb, and that was down. Now we are actually going to replace this one, never use it again, with its two components. So now we have three different vectors. We have the two components from the -3 microcoulomb charge, and we have the one electric field from the 5. So what we're going to do is we're going to find the overall total in the x and the overall total in the y. So let's write that down here. Let's first find the overall total electric field in the x. And in the x direction, there is only one component, which is 25,700 newtons per coulomb. In the y direction, there's two. There's 179,800 up and the 16,058 newtons per coulomb down. So in the y direction, we'll find that total. We have 179,800 newtons per coulomb, which is up. That's positive. Plus, and this is negative because it's down, 16,058 newtons per coulomb. This gives us an overall total in the y direction of 163,742 newtons per coulomb, and the overall is positive, so it's up. Now what we're going to do is we're going to redraw this triangle. We have a total of 25,700 newtons per coulomb to the right, and we have a total of 163,742 newtons per coulomb up. Then we'll find the hypotenuse and also that angle. To get the hypotenuse, we'll use the Pythagorean theorem. And we get the overall magnitude to be 165,746 newtons per coulomb. Now to get the angle, we're going to again use our inverse trig. So we'll use inverse tangent this time. The opposite side is 163,742. And the adjacent side is 25,700. And so our angle comes out to be 81 degrees. So again, for an electric field, it's a vector, so we need magnitude and we need a direction. And make sure that you label that angle or direction on your diagram.